It doesn't really make sense to measure the weight of a shadow because shadows don't exist on their own. They're simply the absence of light. So, measuring the weight of a shadow is like trying to weigh something that isn't even there. Kinda weird, right? For example, right now, I'm using my hand to weigh an invisible Pomeranian. See? Doesn't make much sense. You can't measure something that doesn't exist. But, nothing stops us from stretching logic a bit. We can think of the absence of a Pomeranian as the opposite of its presence. If a fluffy Pomeranian weighs 100 grams, then its absence could weigh minus 100 grams. But negative weight doesn't exist, you might say. Well, even a cheap scale can show negative numbers. Just put the dog on the scale, see it weighs 100 grams, zero the tare, and then remove it. Boom, the absence shows up as minus 100 grams. And the same idea works with shadows. If light has a weight, its absence would show up as a negative value. So, to know the weight of a shadow, first we need to know the weight of light. And that's where the real problem begins. It all comes down to one tricky little word, mass. When we talk about mass in everyday life, we're really talking about rest mass, the mass of an object standing still. If you ask the butcher for 1 kilogram of beef, he'll assume you mean a kilo of beef sitting still, nice and calm. But, if that butcher happened to be studying Einstein's relativity, he might give you a weird look and ask, 1 kilo at rest, or 1 kilo at 90% the speed of light? You'd better answer fast, there are people waiting in line. It sounds absurd that the mass of an object increases as it accelerates. But in daily life, nothing we deal with gets anywhere near light speed. So, for us, mass feels constant. To put it in perspective, the speed of light is over 1 billion kilometers per hour. At that speed, you could circle the Earth 7.5 times in just 1 second. And nothing, absolutely nothing, can go faster than that. Now compare that to a commercial airplane, which barely hits 1,000 kilometers per hour. So, compared to light, everything you know is basically standing still. That's why, in daily life, we only use rest mass. But once an object reaches ridiculously high speeds, something else kicks in, relativistic mass. This extra mass doesn't come from the object getting bulkier or denser. It's the same object, with the same atoms, it just becomes more massive because of speed. So, to sum it up. At rest mass. Near light speed relativistic mass, rest mass plus extra. And the faster it goes, the bigger that extra becomes. The catch is, the more massive an object gets, the harder it is to accelerate. Reaching 100% of light speed would require infinite energy. Which means, impossible. Except, of course, for light itself. The only exception to this whole story is light. Light actually travels at the speed of light, obviously, precisely because it has no rest mass. But here's the catch, when we say light has no mass, we mean rest mass. If light were standing still, its mass would be zero, except it never stands still. It moves at over 1 billion kilometers per hour, which means it picks up an extra factor, its relativistic mass. So in a way, we can say light does have mass, but not the kind you can put on a bathroom scale. You can't just place light on a scale and read its weight. But you can measure the effect of that relativistic mass, radiation pressure. Yes, light can actually push things. A constant stream of photons hitting a surface exerts a tiny pressure, but real nonetheless. That's the weight light puts on objects. Alright, let's play scientist. Imagine a scale with 1 square meter of surface area. If sunlight covers that area, every photon that lands gives a tiny little nudge to the surface. Add them all up, and you get pressure. That pressure can be described by the formula P equals mc, where m is relativistic mass and c is the speed of light. But wait, here comes Einstein with his famous E equals mc squared. Rearranging, we get m equals E/c superscript 2. Plugging that back into the pressure formula gives us P equals E/c. Now, how much energy does the Sun send to Earth? Under perfect conditions, noon, clear skies, right on the equator, about 1,400 watts per square meter. Divide that by the speed of light, 300 million m/s, and you get P is almost equal to 0.000047 newtons per square meter. Or about 4.7 micronewtons per square meter. Translated into scale language, that's around 0.47 milligrams per square meter. Roughly the weight of a human hair. And here's the trick. If you zero the scale with sunlight hitting it, then block the light with your shadow, the absence of light would read minus 0.47 milligrams. In other words, your shadow weighs the equivalent of -1 hair. Congratulations, you've just measured how much you weigh, when you're not there. Thank you very much for following me so far, see you in the next video, bye.